All right, hi everyone. I'm Levon Haroutunian, and I'm an applied AI engineer at Alafia. I'm going to talk to you tonight about AI-powered medical claims auditing. First, I want to introduce you to what we do at Alafia. Our mission is to combat fraud, waste, and abuse in healthcare through medical claims auditing. We do this in a few ways. For managed services, we have a team of in-house auditors with deep clinical expertise that review a wide range of medical claims. To go along with that, we have productivity tools for claim review, including document chat. And finally, the main topic for tonight, we have AI workflows for medical record normalization and claim recommendations. Something that's very important to us is that we have subject matter experts who do these type of audits all the time in-house, and they provide a lot of guidance and inspiration in developing our AI solution. Here's the reason for what we do. There's a lot of wasteful spending in healthcare. Out of $5 trillion annually spent, about $300 billion of that is fraud, waste, and abuse, and another $1 trillion of that is administrative spend. It's estimated that up to 80% of medical claims are billed incorrectly, and more often than not, that results in the patient overpaying. Addressing this issue is critical to reducing healthcare costs for patients and improving the quality of care they receive. Alafia's agentic AI solution directly addresses wasteful spending in healthcare by leveraging AI to eliminate fraud, waste, and abuse and reduce administrative costs. To show you how we think about audit agents, I'm going to use the example of readmissions cases. In a readmissions case, a patient is readmitted to the hospital less than 30 days after being discharged. Sometimes this is unavoidable, especially if they're coming back for a very different reason. However, in some cases, it can indicate that the care they received during their initial stay was insufficient. Perhaps their care did not meet clinical standards of care, or their post-discharge plan wasn't thorough enough, or they experienced a complication that could have been avoided. The primary question to answer in a readmissions audit is, was the patient's readmission preventable? When this type of review is done by a human auditor, they have to have a substantial amount of clinical experience. They have to review multiple documents that are, on average, 1,100 pages to verify a number of different pieces of information. Then they have to apply a set of guidelines based on the insurance policy, the state the care was performed in, and the year to determine if there are any potential savings in the claim. If they find those savings, then they draft a letter to the payer. But if there aren't any savings, there's no outcome for that claim, which means the time they spent on it is wasted. And given that these claims take over an hour to process, that's a lot of time lost. This problem is also challenging for AI. First of all, there are high traceability requirements, meaning that every statement needs a citation to a relevant part of the medical record. These documents are long, scanned PDFs with no standard formats, and the text in them is very different from general domain text. So off-the-shelf components don't work very well. And finally, there's very specialized criteria that you need to apply to be able to make a recommendation. So standard AI solutions like retrieval augmented generation and generic agents don't work very well in this problem space. Our solution leans on clinical experts to define what type of information we need to find in the medical record and what to do with it once we have it. The role of AI in our solution is not to replace clinical experts, but rather to reduce the burden of finding important details so that the auditor has everything they need to make a determination. Here's a high-level view of our pipeline. The input is the claim and the medical record. First, we extract a set of important details based on the type of audit that we're doing. Then we apply an expert-designed decision tree that's configured based on the insurance policy and the relevant standards of care. This leads to a recommendation that tells a human reviewer either that the case is likely to have no findings, in which case it can be auto-approved, or there are potential findings which require manual review to investigate further. For medical record normalization, we have a fact extraction agent. This agent starts with a list of information types that need to be extracted from the medical record. It scans over every page to identify what pieces of information are present on each page, and then produces structured outputs. This includes a self-healing loop. Every type of information we have has a clearly defined schema and validation rules. If that validation throws an error, the agent is prompted to fix it. To ensure the accuracy of our agent, we have a team of human clinical annotators to verify its outputs, supported by quality control agents in the LLM as a judge framework. Once we have the validated clinical facts, we apply a decision tree, which in this case is a flat list. For each node in this decision tree, we either perform a deterministic calculation or ask an LLM to answer a binary question based on a subset of the clinical facts that were extracted. So for instance, the first criteria here is planned readmission. To figure out if the second readmission was planned, we look at the follow-up appointments that were scheduled at the end of the first admission and ask an LLM if any of them account for the readmission. We do a similar procedure for the remaining criteria until we have enough information to say, yes, this should be auto-approved, or no, a human needs to look at this deeper. There are a number of benefits to our approach. For one thing, we are decomposing the task into its atomic parts. Each of these parts can be accomplished by a general visual language model and is straightforward to quality control. It's also modular, which is helpful because different audit types often require the same kinds of information to be extracted. Our recommendations are built on expert-defined logic, which reduces some of the non-determinism inherent in LLM reasoning. And all this results in a very useful bucketing of claims. Some cases are auto-approved, so a human doesn't have to look at them. The other ones are likely to have findings, so now human auditors can spend more time on them. To finish off, I want to do a quick spotlight onto a tool that's been very useful for us, which is structured outputs with Pydantic. This is an example that has been very challenging for me personally. If you ask an LLM, or a VLM rather, to produce the temperature reading here as a string, the answers you'll get will be in a wide variety of formats. Some of them are nice and easy to parse, others are not. Sometimes the VLM will even try to produce Unicode unsuccessfully. And in our case, that led to us not being able to save this data to our database. And here's how you might solve that with Pydantic. First, you define the schema of the type of data you're trying to capture, including types for each attribute. You attach this schema to your prompt to the LLM or the VLM, and when the VLM produces output based on the schema, you can try to instantiate the model to validate it. If you're not able to instantiate it, either because there's a missing attribute or the types are incorrect, it'll throw an error that you can use for self-healing. You can also add your own custom validators to add additional checks at instantiation. For instance, this one checks to see whether the temperature reading is within a reasonable range for a human body. With the thinking here being that if it's outside of this range, it's probably wrong. It's either not a temperature reading or it's a temperature of something other than a human body. And this gives you a lot, right? It's easier downstream processing. So for instance, if you need to figure out if the patient ever had a fever, you can just do a quick numerical comparison. You don't have to do any additional parsing. It also gives you custom validation for self-healing and allows you to use the model schema as instructions. It's further documentation of the type of information you're trying to get. So to recap, Alafia is building AI-powered solutions for combating fraud, waste, and abuse in healthcare spending. And we do that through a combination of medical record normalization and expert-defined recommendations. Our AI agents cut human review time from hours per claim to minutes per claim and allow our auditors to spend more time on claims that are likely to have savings. And our system directly encodes human clinical expertise and is traceable at every step. Thanks for listening.
Cool. Next up, Abhi. So hi everyone, I'm Abhinav. I'm an AI engineer at FlutterFlow, and I'm going to be talking about how we build our new product, Dreamflow. So about me, I'm currently working as an AI engineer at FlutterFlow, where we're building AI-powered models and systems that power Dreamflow, and Dreamflow is a AI-first platform to build mobile apps. And before this, I did my master's at Stanford, focusing on neurosymbolic AI research, before which I was a software engineer at Google, working on account security at Google Workspace. So I'll start with an intro to what our product is. Then I'll talk about how we built Dreamflow, what the challenges we faced were, and how we solved them, before moving on to Q&A. So what is Dreamflow? So Dreamflow is a platform for building Flutter apps, which allows you to develop with 3 different axes. One being agentic development, that is similar to what you've seen with vibe coding with AI building apps. Then you have visual development, so you can directly drag and drop and visualize what you're building in a live preview. And you can also directly edit code in the code editor if you need to. So this video will explain more about what the product is.
Dreamflow brings omni-surface editing tactile. Edit with code or via an agent. Start with a visual canvas where you can interact with and inspect your running app. And adjust any property right here in the UI. Dreamflow is code native, so your code is the single source of truth. And when you're ready to collaborate with AI, just right-click. Add context, share a screenshot, or tell the agent exactly what you want. Dreamflow's agent understands your running app. It's reading your project, searching files, even fixing errors in real time.
Awesome. So that was an introduction to our product, and I'll be talking more about what the challenges were and what the unique insights were while building this product. And I'll try and talk about stuff that is unique to our platform and not about generic coding agents or agents, because there are a lot of resources already available on that. So the first insight we had is that compared to a generic coding agent that needs to sort of be able to build everything, we have this platform that is only going to be used to build Flutter apps. So we want to come up with ways to make the agent's life a lot easier. So the first thing here is to provide the agent with a starting template with a lot of boilerplate code already set up. So these templates have state management, theme, authentication already set up, as well as all the stuff needed for cross-platform deployment already built in. The next is, so whenever the user sends a prompt, we try and augment the prompt with as much useful information as we can. So we're going to send it the project structure, what are the backend functions already available, what are the UI components that have already been implemented. And so providing this information reduces the search space of the agent, and it can answer the user's query a lot faster rather than having to search and gather information. The next point is that because we as a company have been working on Flutter development for the past 4 or 5 years. So we have a lot of expertise built in, just from working on this for so long. So we have our own custom prompt around 400 to 500 lines, just specifying Flutter expertise, such as what are the best practices to follow, what are common pitfalls it needs to avoid, and so on. And finally, context management is very important because in any coding agent, the tool results can become really verbose, and this adds up really quickly, causing context blow up. So we try and use LLMs to summarize past turns and try and maintain the past context as just small, concise snippets of information that we know is relevant towards developing Flutter apps. We also try and have another document with less relevant information that an agent can read from whenever it needs to. So the next insight we had is that unlike generic coding agents, our agent lives inside a platform that is a fully functional development environment. So there's a lot of information we can take from the environment and provide to our agent, to give it more of an advantage. So for example, we have a screenshot tool which can take view what exactly the agent has built from the live preview. And it can keep on iterating and modifying by taking screenshots if it needs to. Similarly, we have an app logs tool which provides actual runtime logs from the debug console. Again, allowing the agent to add debug statements to debug difficult problems or view what are the runtime errors that occurred while running the app. We also have a hot restart tool, so whenever the agent makes code changes, you can use this restart tool to push changes directly to the platform and keep on inspecting these changes and having this iterative loop without having any humans in the loop. Yeah. So the next challenge is that because our platform isn't just for code development, we also have other modules in the platform, such as a deployment to the app stores and Android Play Store. Also, we have modules for connecting to the backend, such as Firebase, Supabase. So you want the agent to be able to assist the users with using the platform as smoothly as possible and go beyond just writing code. So the first thing we set up here is a documentation RAG. So whenever there's any query from the user about the platform, it can quickly query the database to provide relevant answers. Secondly, we have set up MCP tools that connect with Supabase and Firebase. This allows the agent to read information about the tables, the data in these tables, and as well as any backend cloud functions that have been set up. You can also write and deploy using these MCP tools if needed. And this allows the agent to be able to, or the user to remain in one platform and do both the backend and front end part of the development without having to shuttle between different dashboards. Finally, we've tried to add fix with AI buttons wherever possible in the UI. So if there are any code analysis errors, any errors that happen while deploying to the App Store or Play Store, or if there's a runtime crash when you hot restart, we always have a fix with AI button that pops up right next to wherever you are in the UI, and clicking on that button would send all the error logs and information, as well as documentation about the feature you're currently working on, allowing the agent to quickly present a fix or modify any code necessary to solve the problem. And finally, because code development or app development is a really competitive space right now, there are a lot of companies working in this. We need to have tools and processes set up to be able to develop quickly and to be able to deploy to prod within usually even the same day as soon as something new comes out. And we know in the AI world today, there's a new model coming out almost every day, or new research papers that are super exciting and we want to implement quickly. So the first step towards this is having our own custom multi-language model orchestration layer. So we try to not use providers such as LangChain and LangGraph for the orchestration, because we want to be able to make or use new models that come out as soon as they are released. So we can make our own custom changes to our orchestration framework without having to wait for providers to be able to support those models. And also because the majority of our code base is in Dart, being a Flutter app development platform, we also want to avoid depending on any Pythons or C++ libraries. And finally, we need to have a really robust and quick evaluation process. So the first step in evaluation is manual vibe checks. So we set up our own database of prompts across a variety of use cases, and we always test agents on these to get an idea of where they're doing well and where they're doing poorly. And secondly, we've developed our own in-house benchmark for app generation. So AppBench basically contains a lot of different prompts for generating apps, as well as metrics on how to evaluate them. And so we'll generate run all these prompts against the agent to generate apps, and then evaluate them using a combination of LLM-based static code analysis and also computer use agents that actually run the app and figure out whether things are working. Finally, once we are done with manual testing as well as the benchmark, we want to release any experiment we've done to a small subset of users and track metrics to see whether it's doing well. So firstly, there'll be some static metrics such as how often the app compiles after a change, how often the user asks to revert, and how long or slow the queries take to run. But as you can imagine, for something like app generation, static metrics aren't enough, because a static metric can never capture how good the UI quality was or how closely the functions implemented were actually matching the user's request. So for this, we've also set up an LLM-based user sentiment analysis. So what we do is for any prompt the user sends, we take the agent's response as well as the prompts that came before and after it as context, and send it to an LLM to sort of figure out how accurate the response was to the user's query and how satisfied the user was with the response. So then we're looking at this combination of this static as well as the sentiment metrics to see whether something we've tried has done well, and if it is, we're going to release it to a larger set of users in prod. And yeah, so those were insights on building Dreamflow, and open to any questions.
Before I start, can we take a moment to appreciate Lauren and Ponzi team for how well put together this event is? It takes a lot to find speakers and put this event together, so thank you so much for organizing this. All right, okay, so my name is Sid. A little bit of disclaimer. So when I was preparing for this presentation, I put it to ChatGPT and asked for feedback. And it said, you are doing a tech talk, you're not doing a stand-up. So if you find this a bit dry, blame it ChatGPT. Okay, so a little bit about myself. So I currently manage a couple of teams under ML ranking platform at Reddit. Before that, I helped build the initial version of Reddit's feature store. And before that, I was in Bloomberg, working on all parts of model development lifecycle for Bloomberg Law. And by the way, this picture was taken 2 kids and 20 pounds ago, so I don't look like this anymore. Just a disclaimer, this is the reason. Okay, how many of you have, just by show of hands, have used Reddit before? Okay, so I don't have, okay. Can I put you on spot? What part of Reddit do you use?
I use mostly about immigration stuff.
Okay, so you use search?
Yeah.
So you search for things? Okay, so search. Does anybody use home, popular, feeds, subreddits? Okay, so all of that, if you open the app and if you see any post or subreddits that are ranked in a particular order, that is generated through our platform. So that is basically what my team does, is we manage the infrastructure and underlying all of ranking of Reddit. So we serve home, popular, subreddits, search, ads, chat, anything that is in sorted order, we serve that. So almost nearly like 100% of live traffic goes through the system. It is a tier 0 platform, so we have to focus on resiliency and latency a lot, and that's where most of our time is spent. It is a large team. I think we work with 20 different teams within Reddit, around 150 engineers. So we have like our repository and service is very high velocity. We deploy, I don't know, like maybe 30 times a day with like 70, 80 commits going in every single day. So that comes with like, a lot of challenges. Okay, so a quick refresher of what ranking is. If I'm just being like very hand wavy, ranking can be done in 3 big stages. So we have candidate generation. We have, let's say, a few million posts that are created. We narrow the pool down for a particular user to, let's say, several thousands. And that's the candidate generation piece. Then we have filtering. So based on your preference, you would narrow it down further. So if you don't want to see a particular subreddit, you have blocked something, we would remove that. And then the third part would be scoring, where we actually send those candidates to a machine learning model, and that model is gonna, or a heuristic formula, that model is gonna give a score, and we use that score to sort candidates and give it to you. So to support these 3 ranking steps, we can divide like our platform into 4 big components. Our platform, so the first component is the API that clients interact with, and it's not just the API that like you'll call the service with. That API is integrated throughout the stack, and as I'll explain just a little bit more in details later. Then we have data stores and indexing. Now these data stores basically powers the candidate generation piece. So if you are making a complex query of, okay, I want a post created in last 1 hour, created by like users in Europe, that's where like these indexes and data stores are useful. Then we provide a lot of custom DevX tooling. Now this tooling is help engineers move fast. So like when you have a new idea or new concept of a ranking, we will help you move fast with all the DevX tooling that we provide. And caching is tied to the resiliency piece, so it also speeds up the platform. Of course, like caching is used for that, but we also use that as an availability booster. So anytime our dependencies go down, if we have data cached, we don't have to go down, because it is a tier 0 platform. Like we spend like a lot of time thinking about caching, and caching is almost everywhere. Like anytime we go outside of our platform to fetch any data is basically backed by a cache. All right, okay. Let's talk about the API. So API is pretty simple. We only have one type of method. It's called rank. It takes in a request and it returns a request. It's the same object. So request object basically contains everything we need to generate a feed and also to return a feed. And I also want to introduce a concept of stage. So stages are basically building blocks that you can that we provide to our users. And these building blocks does like one action and one action only, tied to the 3 steps of ranking that I said before. So either it could be a candidate generator, it could be a filtering stage, or it could be a scoring stage. Now a stage processes, as you can see, like we send the same protocol of request in the stage. So stage takes in the request, either adds, removes, or modifies that request in some way, and then returns the same request back. Now what allows us to do this is like you can change stages one after the other, and you don't have to worry about input or output of a particular stage. So any stage, and I'll go into an example after this, but this makes the platform very flexible, and you can reuse stages and attach stages one after the other without having to worry about input or output. Okay, so this is an example pipeline. This doesn't exist in real life, but as you can see, so what we are doing is we are fetching 3 candidate sources, fetching popular post, video post, and image post, and then merging those candidates. And once we have those candidates merged in, we will remove everything that you have already seen and score candidates. So use some machine learning model to score them, and then sort them and return the request back to user as a feed. Okay, so this is the code for the same pipeline. Now it sort of makes sense. We have a parallel stage. Now that is going to execute these 3 stages: a popular post, fetching video post, and fetching image post in parallel. And after that, Once all of these 3 stages are executed, we will apply the filtering and scoring and sorting, and then we return the feed back. Now, as you can see, like this makes the definition of a ranking like pretty straightforward. So you don't have to worry about you don't have to look at a lot of code to understand what is the business logic of the pipeline. Anytime a user needs something custom, they can write their own stage, and we incorporate that into our platform. We have like hundreds of stages already. So you pretty much any new ranking that you have to generate, you can just pick the stages you want, and in one file you can have your ranking pipeline. All right. So with the API, as I said, all the customers have to do is to define the ranking logic with existing stages, and the rest of the plumbing is already connected. If they require, as I said, if they require business logic that doesn't exist, all they have to do is write new stage conforming to that API, so that stage can be in future plug and play into any other pipeline that they want. All right. In ecosystem of tools that we provide to our users, we provide a lot of tools. I think the most interesting one for this particular audience will be candidate indexers or candidate generators. Now we have a whole team supporting this initiative, making tools for people to make unique candidate sources. You can imagine this is the offline workflow that we need to do before actually ranking is done. And to give an example, does anybody use subreddit, go to a subreddit and change sorts? Okay, what sort do you usually go to?
Oh, do you mean when I'm looking for posts in a particular subreddit?
So if you browse a subreddit, you can change sorts on the subreddit. So
okay.
Yeah.
Because sometimes I want to go by new, right?
Yes, exactly. Okay, so let's take new as an example. So if we want a data source per subreddit that gives us posts sorted by new. So what we would do is we will consume an event, let's say a post create event. We'll look at the timestamp and we maintain a sorted list by timestamp of all the posts that are created in that subreddit. So then you can find those newer posts at the top of the stack always. Right now, anytime you want to serve a feed through that, you can just say, okay, give me post for this particular subreddit for new sort, and we give that back at the serving time. And this is the place where we started introducing LLMs in the offline workflows. And I'll go into detail about a couple of ways that we do that. So we have a streaming LLM framework where we consume side events. It's pretty standard. We consume side events. We have a prompt generator. Now, what prompt generator does is I'll give you an example. Let's say you want to categorize posts as political or not. That's a very difficult thing to do. So we will consume post create events, and anytime a post is being created or commented on, we can take the post title, post body, and some comments, and we generate a prompt which combines all those information and then put that message onto Kafka, where LLM can use that prompt and give an output. So in the LLM inference consumer, we don't actually have to go outside anywhere except to make the LLM call. And then we can store that data yes or no, whatever LLM says, to a data store. So once it's written, it can be easily accessed in any of the ranking pipelines you want to use. We also provide a fallback mechanism in case you reach quota with one of the LLMs that you want to use. This happens a lot because every team has a budget, and so they will say okay, we can only support this much throughput and this much budget. So after Gemini quota is run out, use some internally hosted LLM. So we provide that template, we templatize that, and we provide that capability to our users. So batch framework is very similar. Instead of Kafka, we just read from BigQuery, and we have a consumer that is priority-based consumer. So that consumer basically manages the budgeting, so backfill doesn't get into the way of actual cron job, and that's gonna the one Kafka consumer that you see is gonna make sure that anytime Gemini or any other LLM is returning errors, they would go or you run out of quota with them, they will go and go to the fallback. Okay, so this is also a pretty cool offering of our platform. This is a dashboard with like all sorts of debugging information. You can find, you can execute pipelines for internal users. You can look into candidate generators, look into actual data stores, and compared to pipelines, we also have a tool. This is pretty cool. I don't have a slide for this because legal didn't approve it, but because it shows like an actual pipeline that we have in production. But we provide a DAG view of any pipeline that has been executed, and you can click on those nodes to see like what input went into a stage and what output of that stage. So you can exactly like answer. So in recommendation system, like it is very difficult to answer like why my feed looks this way, like, or why am I not seeing this subreddit in my feed? But if you have that DAG view, you can click into stages and see where that subreddit was dropped and why it was dropped. So it provides a enhanced debugging capability. Okay, so for resiliency and safeguards, as I said, the platform is tier 0. I don't know, 100 million people or so, like I mean tens of millions of people use this every single day. So we need to make sure that it is up and we can't mess up. So we have a whole array of tools to make sure that the platform is up. I'm gonna go over, like very quickly go over 3 of them. The first one is adaptive concurrency limiter. Now that is, in a nutshell, I mean you can read about this, it's pretty interesting, but in a nutshell what it does is when a server is not healthy and it is returning errors, the adaptive concurrency limiter is going to start pushing back on requests until the server becomes healthy again. And once it becomes healthy and doesn't return error anymore, then slowly it's going to increase traffic to the server. So now, like yes, we are returning errors, but we are also protecting our dependencies. So we are not going to like hammer a node that is already bad. We are just going to like back off, and this will like have like automatic back off and then retry. We don't have to like manually do anything. Another part of this, I think I briefly touched this, caching. So we have a 3-layer, multi-layer cache. Anytime we go outside of our platform, the call is cached, and this gives us a lot of resiliency because our dependencies can go down and we can survive in a degraded state. If a dependency is extremely critical, we put multi-layer caching. If it is not as critical, we don't spend that much money. So it's basically configurable on the platform on like what type of caching you need. But anytime we go outside of the platform to get any data or service call, like all of that is cached. And live config is pretty straightforward. I think you might have used that in your work as well. It's just a feature flag system. You can put any flag with any configuration that you can change during an incident. So let's say I want to reduce my cache size or don't want to send data to some Redis cluster. You can very easily do that with this. So during an incident, this becomes very easy. Let's say a downstream dependency is having an issue. We can just shut off traffic to that dependency. If we can survive without it, let them recover, and then we can turn it back on without actually deploying any code. I think that's it. This slide basically says Q&A. I'm happy to answer any questions. Thank you.